index by Lévy trees.
Thank you, Ines, for the introduction, and thank you very much for the invitation. I'm very happy to be today in the seminar. So today I'm going to present a collection of results that we obtained recently in two works with Armand Riera from Sorbonne Université that we refer broadly as an excursion theory for Markov processes which are indexed by random Lévy trees. So I will not assume that you are familiar with the objects that I will be manipulating. So I will start slowly by giving an informal introduction to the notion of Lévy trees, as well as to the one of a Markov process indexed by a Lévy tree. And I will as well afterwards recall some classic facts on excursion theory for time-indexed Markov processes. After that, I will present you the two kind of main pillars of the theory that we developed. And afterwards, I will spend some time on applications so that you have a bit of a flavor of the type of results that you can obtain by making use of this type of results. And don't hesitate to stop me if something is unclear or you want me to go back to clarify any notion. Okay, so then I will start by introducing informally what is a random Lévy tree. So Lévy trees are a very rich family of random fractal trees, which are constructed in terms of excursions of a sub-collection of Lévy processes reflected at the running infimum with no negative jumps. So we say they are spectrally positive. So some notable examples that you have encountered before are the Brownian tree or the CRT with free total volume, as well as more generally alpha-stable Lévy trees. So the theory was developed mainly in two works, one from Gall and Le Jan on 98, and afterwards another work of Duquesne and Le Jan in 2002. And after that, there has been a lot of progress in the theory of Lévy trees. The theory has been expanded in many directions. And at this point, there are a canonical probabilistic object, which is very well understood. And they are as well universal in the sense that they arise as scaling limit of large classes of Galton-Watson trees. So what I will do now is I'm going to explain you how do you construct this family of Lévy trees in terms of excursions of reflected Lévy processes. So I'm going to note by psi the Laplace exponent of a Lévy process with no negative jumps and paths of infinite variation. So if you are, I mean, it's a bit more than this, but if you are familiar with the theory of branching processes, we want the Laplace exponent to satisfy that the associated branching process dies in finite time. So here in the left, I am considering an excursion of my reflected Lévy process that is running infimum. And now there exists a functional of this excursion, which is rather complicated, and it's called the height function, which transforms this excursion into a continuous path. So the way this functional works is rather technical, so I'm not going to enter in the details. But if you are familiar with the theory, the discrete time theory of Galton-Watson trees and Lukasiewicz walks, the relationship between the height process and the excursion is similar to the one between the Lukasiewicz walk and the counter function. But now that we have this height process constructed in terms of the excursion, we are going to make use of canonical tools to construct the tree coded by this height function. And the informal idea is as follows. So informally, what we're going to do is we're going to put glue below the trajectory that we are considering the right. So you put glue below this trajectory, and then we fold it on itself. This is going to glue any pair of points that can be joined by a horizontal line without crossing the black path. Then if we perform this gluing, we obtain what is called as the psi-Lévy tree, coded by the height function h. Okay. So this description is informal, but it can be made rigorous by making use of some equivalence relation. So this can be done for any psi Laplace exponent. So we have, in fact, a family of random Lévy trees, a rich family of random fractal trees. So now let me turn my attention to a particular case, which is particularly simple, which is when the Laplace exponent is quadratic. So it's the Laplace exponent of a Brownian motion, or maybe a constant times some Brownian motion. So in that case, the excursion of the reflected Lévy process that is running infimum is just a non-negative Brownian excursion. So this is what I'm simulating in the left of my slide. Then in this case, well, the excursion is of course already continuous. And if you apply this height functional to this excursion, actually the height functional doesn't change anything in the path. So in this case, the height function is superfluous, and this simplifies a lot the study in this particular case. So one doesn't need to introduce this shape process to study the tree associated to this excursion. Now I can perform the same construction as before by putting glue below my trajectory. And then I fold it and I obtain a very particular case of a Lévy tree, which is the so-called Brownian tree. So here you have a simulation. And you can see from the simulation that the geometry of this Brownian tree is quite different to the classical geometry that you obtain for more general classes of Lévy processes. So for instance, in the Brownian tree, there are only branching points of multiplicity tree. So what I mean by this is that if you remove a branching point, any of such branching points, you split the Brownian tree in 3 connected components, okay, and exactly 3. And those are all the type of branching points that you have in the Brownian tree. In contrast with the general case that we discussed before. Oops. But here in a typical Lévy tree, you have these sort of hubs that you see, which are the branching points of infinite multiplicity. So this means that if I remove this branching point, I'm going to split my tree in infinitely many connected components. And typically, for your typical Lévy process, say, this collection of infinite multiplicity branching points are dense in the tree. So in the end, the geometry of the tree that you obtain at the end of this construction is highly influenced by the path properties of the Lévy process that you started with. Okay. So with this, I'm done with my very brief overview on Lévy trees. And now I'm going to discuss how do we construct the notion of a Markov process indexed by the Lévy tree. So the idea is that instead of considering Markov process indexed by time, now time is going to be random, and is going to be substituted by one of these random Lévy trees. So the idea is conditionally on a Lévy tree, we're going to consider a continuous Markov process, which at the root of the Lévy tree starts at some point of the state space. And then we're going to let it travel along the branches of the Lévy tree, away from the root. And the only rule is that at each branching point of the Lévy tree, it's going to split in independent copies that continue to evolve with the same dynamics. Okay. So, I mean, this is an informal construction, but it can be made rigorous by using the technology of the Lévy snake. Now, for concreteness, in my talk, I'm going to often present my results in terms of the Brownian tree. So when the Lévy tree is this Brownian tree, and when the motion is an R-varied Brownian motion. And the corresponding tree indexed process is the so-called Brownian motion indexed by the Brownian tree, and it is denoted in this way. So BA indexed by tau h. But everything that I'm going to say, up to some details, are going to hold for more general class of Markov processes with values in some Polish space, and large classes of Lévy trees. So from time to time, I'm going to still say a word on the general case, but my slides are really thought in the Brownian case because it simplifies quite a bit some presentations. So just to have a bit of a picture in mind of this Brownian motion indexed by the Brownian tree. So on the left, I have, again, my Brownian tree. And in red, I am highlighting a geodesic which connects the root of my Brownian tree. So this is this point over here. I'm not sure if you can see my mouse. Hopefully, yes, super. Okay, so this is the root of the Brownian tree. And in red, I have a geodesic path which connects the root of the Brownian tree to a leaf. Okay. And now, well, essentially by definition, if we look at the values of Brownian motion indexed by the Brownian tree along this geodesic path, what we see is what I have in the right. So it's a Brownian path, which at time t equal to 0, it's equal to 0. Then it evolves as a Brownian motion, but this Brownian motion has finite duration, and the duration is exactly the distance between the root and the leaf A. Okay, and we have this along all the paths of this Brownian tree, and that's the picture to have in mind for Brownian motion except for the Brownian tree. But now, especially for presentation, it is often to have a picture in mind of the process all at the same time, so that we can see all the paths together. So in order to represent this object, I usually use this type of pictures, and not only myself, but co-authors as well. And this should read as follows. So the point that you have over here is the value of my Brownian motion at the root of the Brownian tree. Then if I follow any of these paths, for example, this one, this corresponds to looking at the values of B along a geodesic path up to a leaf. Okay. So this would correspond to looking, for example, at this geodesic path and looking at the right at these values. But now, because we are looking at all the values at the same time, well, this path is going to branch at the left and at the right, and those branching points correspond exactly to branching points in the Brownian tree. Okay. So in the end, the branching structure of my process is governed by the branching structure of the Brownian tree, and the behavior of the labels is governed by the law of the Brownian motion. And the same description holds if you change the motion by some abstract Markov process, and the Lévy tree, by instead of being a Brownian tree, to be an arbitrary Lévy tree. Okay. So we have these two kind of layers of randomness. So with this, yes, so just one last notation. So I will be denoting by n the law of this tree-indexed process. So notice that because the Brownian tree is defined in terms of a non-negative Brownian excursion, which is defined under an infinite measure, this law n is going to be an infinite measure, and it is not a probability measure. And this, in fact, is a bit can be a bit problematic. So it will be convenient to have as well some sort of description of this object, but under a probability distribution. And this can be done up to some details that I'm going to explain now. So everything that I have explained before about the construction of the Brownian tree holds if instead of considering a non-negative Brownian excursion, I replace it by the whole reflected Brownian path. So this is what I'm simulating here. So this is a simulation of a reflected Brownian motion. And in particular, each of these excursions is a non-negative Brownian excursion. Now, if I perform the same construction as before in this path, then I will have something that we call a forest of Brownian trees. And the reason is simply that because each one of these excursions is an excursion of Brownian motion, a negative Brownian excursion, if we perform the gluing to each one of these, what we obtain is a Brownian tree. But we're doing this for all of them at the same time. So in the end, what we get is no longer one Brownian tree, but rather an infinite collection of Brownian trees. And for this reason, we call it a forest of Brownian trees. And these Brownian trees are glued at the root, essentially by construction. Okay. So now I can perform the same construction as before. I can consider Brownian motion indexed by a forest of Brownian trees. And the law of this tree-indexed process is going to be denoted by P. So in this case, it is a probability distribution because the law of reflected Brownian motion is a probability distribution. Okay, so with this, I am done with this informal description of tree-indexed processes. And now I'm going to recall some classic facts on excursion theory, and I'm going to actually focus in the Brownian case. So this is, again, to simplify it with my presentation. So here I'm denoting as well by B with T in R plus for an valid Brownian motion under some probability distribution. And in the theory of Brownian motion, there is an additive functional, which is kind of crucial in the study of Brownian motion, which is its so-called local time at zero. So this local time at zero, it is denoted by L. And at each fixed time t, it is defined according to the following approximation. So informally, if you have never seen this object before, the local time at time t is measuring how much time Brownian motion spends at zero up to time t. So this description is informal because the Lebesgue measure of the set of times at which Brownian motion takes the value 0 is 0. But if you renormalize things properly, you can make sense of this notion in a fractal sense. Now, I will be denoting by AI and BI for the connected components of the set of times at the complement of the connected components of the set of times at which Brownian motion takes the value 0. We call these excursion intervals. So for example, here you have one of such excursion intervals. So it's an interval where at the left, the Brownian motion is taking the value 0, at the right as well. But in between, it is not taking the value 0. And now the excursion associated to the excursion interval AI-BI is going to be denoted by B star I. Okay. Now, the main result of the theory states of excursion theory, which is in the Brownian case due to Ito, states that if we consider the point measure with coordinates first the excursions, and then in the other coordinate, the amount of local time spent at 0 by Brownian motion up to the start of the corresponding excursion. And this point measure turns out to be extremely simple nature. It's just a Poisson point measure with intensity, the Lebesgue measure, times some infinite measure that it's called the Ito measure, Ito excursion measure for Brownian motion. So again, if you have never seen this result before, the way you should interpret it is that if we look at the excursion of Brownian motion ordered with respect to the order induced by time, the excursions are independent, and their law is this measure n. So this, this statement has to be interpreted appropriately, but this is the rough idea. But keep in mind that this measure is an infinite measure. Okay. Okay, so this is one aspect of the theory, but for us, it will be important to as well have a good understanding of another closely related family of Brownian paths, which are very related to the excursions. So this is the following. So now I will be interested in no longer just excursion, but actually Brownian paths shifted at starts of excursion debuts. So just to have a picture in mind, so imagine that we look at the excursion interval AI-BI. The left-hand point is what we call as the excursion debut, which is here. And then I will look at Brownian motion shifted at this excursion debut time. So it's this whole path. In particular, if we stop this path vi up to its first return time to 0, we recover the excursion b star I. So bi contains strictly more information than the excursion b star I. Okay. Now we can perform the same game with the local time. We can consider the local time L shifted at the start of an excursion interval, and this is going to be denoted by Li. So now we have this family of bi's and li's. And now, well, kind of in the same flavor as before, we would like to make sense to the notion of the law of this family of paths. So before, this role was played when we were dealing with excursions. This role was played by the excursion measure n. And now we want to obtain some similar description for this family. But now, of course, because this family depend a lot on each other, you cannot really expect that they will be of Poissonian nature. But you can still make sense to the notion of the law of a typical element of this family in a weaker sense. So if you want, in a many-to-one type of sense. And this is what the exit formula is going to give us. So the exit formula, in this case, tells us that if we consider functions which depend on this family of shifted paths of Brownian motion, and we take expected value of these type of functionals, then this is a very simple form, because it's just an integral of this type. So I think the only thing that you need to remember about this is that the function f is being integrated in the right with respect to the infinite measure that I'm denoting by n infinity. So informally, this is telling us that the typical element of this family of shifted Brownian paths is distributed according to this measure n infinity. And the measure n infinity has a very simple description that now I'm going to give, and that you will not be surprised given the construction of these shifted paths. So the measure n infinity is nothing but the concatenation of an excursion of Brownian motion, this is in red, with an independent Brownian path started at 0. So I think informally it is quite intuitive that this should be a good candidate for describing the law of this family of shifted paths, but this exit formula tells us that it is indeed the good candidate. Okay. So with this, I am done with the preliminaries that I will need to introduce the results. And now I can go back to the original problematic. So the goal is to obtain, if you want, some sort of analogous theory, which now describes the structure of the excursions away from a point for Markov processes indexed by Lévy trees, as long as we have a point which is what is called a regular and instantaneous for the motion. So in the Brownian case, for example, 0 is a regular and instantaneous point. So if you have never seen this notion before, you can really stick to the Brownian case, and the point would be 0. So it is important to mention that an excursion theory was developed before and by very different methods. In the case of Brownian motion, they say by the Brownian tree, in a work of Gall and Abraham and Le Jan in 2018. And the results of this paper have been used a lot in recent years in the study of Brownian motion indexed by the Brownian tree, as well as in other fields such as the so-called Brownian geometry. So kind of the success of this work motivated Armand and myself to expand this theory to much more general classes of tree-indexed processes. But it is important to mention that the methods that we employ are completely different to the ones of Abraham and Le Jan, due to the fact that the theory of Abraham and Le Jan relies in many symmetries and scaling properties of Brownian motion indexed by the Brownian tree. And you lose all of these as soon as you consider a more general Lévy tree and an arbitrary Markov process. So we had to proceed completely differently, but we actually managed to record the results of Abraham and Le Jan in the Brownian case, and actually more precise version of their theorems. So I will go back to this later on. Okay, so just to recall a bit the notations that I'm going to need. So remember that Brownian motion indexed by the Brownian tree is denoted by this as in this form. This is the tree indexed process. That N stands for the law of Brownian motion indexed by a Brownian tree. And then P stands for the law of Brownian motion, but now indexed by a forest of Brownian trees. And we said that P is a probability distribution, while N is an infinite measure. So now I'm going to give some constructions under both N and P. But again, if you are familiar with the more general theory of Markov process and Lévy trees, you can pick your Markov process of choice as soon as there is a point which is regular and instantaneous, as well as your favorite Lévy tree. Okay, and essentially everything that I'm going to say holds up to some slight modifications. Okay, so now I'm going to start then with building towards our first main result, which is a Poissonian description of the excursions of Markov processes indexed by Lévy trees. So in order to do that, I will first need to introduce analogous notions to the one that we have introduced before. So for instance, the notion of an excursion component or an excursion even, we need analogous definitions in the tree indexed case. And this is what I'm going to do now. So first, I will be denoting by I for the set of points in the tree at which the motion, the Brownian motion, say, takes the value 0. So in my representation here, I'm representing, say, the Brownian tree, and I'm putting in yellow the points at which my Brownian motion takes the value 0. So, of course, this is not a discrete set. It is actually a very rough and complicated subset of the GT. But just again, for representation purposes, we think of it as some sort of discrete set. But it is not at all the case. Okay, and we will go back to the structure of this set in the end of my talk. Now, the excursion components is going to be defined just as the closure of the connected components of the complement of I. So let me explain. So if I remove the set of yellow points from my TT, from my tree T, so here I still have the yellow points, here I have removed them, then I am cutting my tree in a collection of connected components. For example, you have one here, have another one here, and the closure of each one of these is what I call an excursion component. Okay, so here in blue, I'm highlighting one of these excursion components, and in each one of these, I have a point in this component which is closest to the root of my tree T. Okay, and this point here is what I call an excursion debut point. So I will use always the notation U for denoting excursion debut points. I will use the notation D for the collection of excursion debuts, and for each excursion debut, I will denote by CU the corresponding excursion component. So if you compare it to the time indexed case, it's the same definition as in the time indexed case, where excursion components were the connected components of the complement of the set of times at which the motion takes the value 0. So here is the same definition, but in the tree indexed setting. And now excursions are going to be defined in a very natural way. So the excursion associated to the connected component, excursion component CU, is nothing but the restriction of the motion to the component CU. Okay. So I think it's the very natural way to define the excursion. So to have a picture in mind, what should you imagine when we think of these excursions? Well, it's something that looks roughly like this. So again, let me explain. So the point in here corresponds to the value of the excursion at the root of the excursion component. So if you want, at the excursion debut point. Then if I follow one of these paths, this corresponds to looking at the values of my excursion along a geodesic from the root of the excursion component up to a leaf. And now two things can occur. If I continue my traveling, maybe I will go to a point at which the motion returns to 0. Okay, so this would correspond to a point like this, which are highlighted in yellow. So in that case, the path has to end there by definition of the excursion component. But another possibility as well is that I'm traveling along one of these paths, and actually, well, the component ends before the motion can return to 0. Okay, so that's as well another possibility. And in particular, the set of points at which the excursion returns to 0 is again a very complicated subset of the excursion component. And again, we will go back to the properties of this subset later on. But for now, I'm not going to discuss it. Okay, so now that we have defined the notion of excursions away from 0 for the tree indexed process, we are going to need, much like in the setting of time indexed processes, some local time process to index them, to obtain a result which is analogous to the one of Ito for Brownian motion. But in order to do that, I will first need to introduce a notion of order for the points in my tree. So to do that, I will make use of the so-called clockwise exploration of the tree T. So the clockwise exploration of the tree T is a process indexed by time, which at time t equal to 0 starts at the root of the tree. And then as time increases, it's going to move along the branches of my tree, following the contour from left to right. So this gives us a way to explore the tree in an ordered way. And in particular, it induces an order in the tree, which is some sort of lexicographical order. So now that we have a notion of ordering the points, our first work, which consisted in the following. So we proved that there exists a continuous non-decreasing process that I'm denoting here by A, which essentially grows each time that the clockwise exploration of the tree encounters yellow points, so points at which the motion takes the value 0. So again, you should think really this in an infinitesimal way, because this set of yellow points is uncountable, so everything is in a fractal sense. So this process A is really as close as it gets to a local time process in the training dataset setting. So let me just to make sure that it's clear to explain again how this process A works. So at time t equal to 0, the clockwise exploration is here at the root of the tree T. Then it starts traveling from left to right, and eventually it will encounter yellow points at which the motion takes the value 0. And every time it encounters yellow points, the process A is going to increase infinitesimally, much in the same speed that local time at 0 increases every time Brownian motion takes the value 0. Okay? So this is our local time process in the tree index setting. And now just one last notation. So for any debut U, I'm going to denote by G of U for the first time at which the clockwise exploration of the tree visits the excursion component CU. So again, let me explain the picture. So imagine that we are looking at this excursion component CU. Then the clockwise exploration of the tree is visiting my tree from left to right, and eventually it will enter the excursion component CU for the first time. And that's exactly G of U. Okay, so now I think I have everything I need to state our first main result, which is a version of Ito theorem in the tree data setting. So we prove with Armand that when working on the probability distribution from P, and this is important, not under N, but under P, if we consider the point measure, which consists in the excursions, but we are going to index them by the corresponding value of this local time process, this is just a Poisson point measure, and with intensity given by the Lebesgue measure times some infinite measure that we call the excursion measure away from, well, in this case, away from 0, but more generally away from the point X that we might be looking at. Okay. So in particular, and now this measure N star really describes the law, if you want, of a typical excursion of Brownian motion except for the Brownian tree, or of the Markov process of choice indexed by the Lévy tree that you have chosen as well. Okay. So this result is already surprising and of theoretical interest, but actually in practice, if you don't have a good understanding on what is this measure N ball star, there is very little applications of it, because in practice, if you want to perform some sort of explicit computations or perform more fine analysis, you need to have a very good understanding of what is this measure N ball star. And up to now, I have not given any reason to say that this measure is simple. But now, so what I'm going to do now is actually convince you that it is. It is a very simple object, and we have a very good understanding of it, as well as many tools to work under this. But in order to convince you of this, I need to actually do a bit of a detour and go through the second main result that we obtained, which concerns a version of the exit formula, but in the tree indexes setting. So again, we kind of go back to a little bit. So here again, I have a representation of my Brownian tree or my Lévy tree. In blue, I'm looking at an excursion component CU, and in red, the corresponding debut point. So now I'm going to be interested to another subset of the tree T, which is associated to the debut point U, which is what I call the subtree, which stems from U. So this is defined as the collection of points which are children of U in the tree T. So if you want, this is all the points which have been highlighted in green in my slide. Okay. So of course, notice that the excursion component CU is contained in the tree TU. So TU has strictly more information than the excursion component CU. And in particular, I can recover CU just by truncating appropriately the subtree which stems from U. And now, again, in the same spirit as we did with excursions, we can define a collection of paths which consists simply in the restriction of our motion to the subtree which stems from U. So this is exactly BU, the restriction of B to TU. But here, actually, it will be of interest to consider, as well as the Brownian motion, the local time of the motion on top of the tree. Okay. So this should not be confused with the process A from before. This is really the local time of B along the branches of the tree. Okay. So BU and LU stands for this restriction of my motion to the subtree which stems from U. And we have one of these for each U. So again, a picture of how you should read this type of trajectories. So notice that by definition, this BU-LU, well, because by definition of TU, this component starts with CU, the excursion component, then BU is going to start with an excursion away from 0. This is exactly what you see here. We have the excursion CU. But then, because we're no longer truncating the excursion at its return time to 0, what we see here are, well, trajectories that live after the excursion has returned to 0. So these trajectories would correspond to the values of the motion along this, the children of points of the excursion setting that come after the excursion. Okay. So in particular, notice that given a BU, I can recover the excursion BU star by cutting everything that has returned to 0 before the end of the respective lifetimes. Okay. So I'm going to denote by TR this trimming operation on BU. So I repeat again. So this is BU, which is the restriction of B to the tree which stems from U. And then if we remove all these trajectories that have returned to 0 before the end of the respective lifetimes, so we trim them, we recover the excursion BU star. So BU has strictly more information than the excursion BU star. So now the goal is, again, in the same spirit as before, to obtain some sort of description to the law of this family of subtrajectories, BU and LU. Okay, but again, kind of like we described before in the Brownian case, you cannot expect that these are going to be of Poissonian nature, but we're going to be able to make sense of these by some sort of averaging formula, and that's going to be the exit formula. But now, in order to do that, I will first going to need to introduce a candidate for the law of these shifted paths. And that's what I'm going to do now. So I will be denoting by in bold a new measure, an infinite measure, which is defined according to the following. So I'm going to consider first a Brownian tree, and then on top of this Brownian tree, I will consider a Markov process with distribution, the measure n infinity. So remember that the measure n infinity consists in the law of an excursion concatenated with an independent Brownian path. Okay, and I can consider the corresponding tree indexed process. And I will be denoting still by B and L under the measure n for this tree indexed process. Okay, so this is our candidate for the law of the typical element of this restriction to the subtree which stems from U, which I think is quite natural given that first we start with an excursion and then, well, at least theoretically, we should have a Brownian path concatenated. Okay, but now I'm going to justify indeed that this is the good definition for this collection. And this is the exit formula. So let me explain. So here I'm considering sums over debut points U, and I'm considering functionals which depend on one hand on the restriction of B to TU. So that's in green. But actually, I'm going to do more than that. I'm going to consider as well another functional which depends on the restriction to the complement of the subtree which stems from U. So basically what I'm doing is for each debut point U, which is, for example, this one, this is cutting my tree in two big components, the green part and the orange part. And I'm considering a function which depends on the restriction to the green part and a function which depends on the restriction to the orange part. Okay, and I'm summing over all the debut U. Okay, so this is in some sense giving us a very complete description on the object when you put yourself at the debut of an excursion. Okay, and now well, it turns out that this type of things are very simple because we have the following description for them. So again, let me explain. So first, the first thing to notice is that the function g, which is dependent on these restrictions to the subtree which stems from U, is being integrated in the right-hand side by the measure n bold. So informally, this is telling us that indeed the typical element of this family of shifted, of subtrajectories is indeed distributed according to the measure n bold. Okay, so this might not be as surprising given the definition of my BUs and LUs, but what might be a bit more surprising is what occurs with the orange part. Because you see, in the orange part, in the right-hand side, the trimming has disappeared from the treaty. So we are forgetting the fact that we trimmed an entire component from the treaty. So the law that you obtain here is extremely simple again. The only price to pay is this bias by the additive functional A, which comes from the fact that essentially you have observed here a typical excursion debut point. So that's the thing. But in the end, then both sides are of extremely simple in nature. Here is Brownian motion except for the Brownian tree, and here the measure n bold, and we have a product. So essentially, you should think that they are independent, more or less. Okay. So an important consequence of this result is that we have a very simple description for the excursion measure n bold star, because it is nothing but the law of B truncated. So remember that TR stands for this trimming operation, where we cut all the trajectories that have returned after return time to 0, under the measure n bold. So this is in particularly important because the measure n bold is very simple. It's a Brownian tree, which is an object that we understand very well. And on top of it, we have a Markov process with this measure n infinity, which again is a very simple object. So we understand very well the measure n bold. And then n bold star is just the push forward of n bold through the trimming operation, which again is extremely simple. So if you need to do computations or analysis on the excursion measure and star, actually, basically what you do is you work on the enbold, you perform your analysis, and then you make sure to transfer it appropriately on the star by taking the streaming operation. Okay. So this justifies that this measure star is, with this description, is really simple. And here you have some sort of sketch of proof, but okay, I'm not going to enter in the details. So now what I want to do is to give you a bit of a flavor. So with this, I'm really kind of done with the two big results of the theory. And now I want to give you a bit of a flavor of the type of applications that are being developed or have been developed using this type of tools. So the first one, which is actually the one that I'm going to spend the rest of my talk discussing, is a description for the law of the excursions conditionally on a tree that I call the tree coded by the local time. So let me explain what I mean by this. So in the time indices setting, when you consider the inverse local time of Brownian motion, it is classical that this is a subordinator. And the jumps of this subordinator are exactly, the jump sizes are exactly the durations of the excursion of Brownian motion. So as a consequence of this, one gets that conditionally on the inverse local time process, the excursions are independent, and their law is just the Ito measure conditioned to have duration, the corresponding jump size. So here we want to have some sort of analogous description for the excursions. But the role played by this inverse local time, which in the time index case is a process, is going to play now by a random tree, which is this tree coded by the local time that I'm going to introduce in a moment. But so before I expand on this, I want to mention very briefly another application which is currently in the works, which concerns the study of growth fermentations which arise when you explore random stable geometries from a point or from a boundary. So the Brownian case was studied in a previous work of Gall and Armand in 2020. But the main tool one of the tools that were used to explore this problem was this excursion theory from Gall and Abraham. But now that we have expanded the excursion theory to large classes of Lévy trees and Markov process, actually we are able to expand the results of this work to more general settings. So more than this, actually, what we do is we identify the so-called self-similar Markov tree in the sense of the recent work of Bertoin, and Riera, which codes the genealogy of the growth fermentation process, which is hidden behind the explorations that we study in random geometry. So again, I'm not going to expand on this anymore because this is really work in progress. But this is another type of application that can be studied using this type of results. So now then, I'm going to really focus on the first application, which concerns in this description of the excursions conditionally on the so-called tree of local time. So roughly, the objective is to introduce a random tree that I will be denoting for the rest of my talk by this totilde, which encodes solely the set of points on the original tree T at which the motion takes the value 0. And we want it to encode as well the genealogy. Okay. And then afterwards, we're going to obtain the description of the excursions conditionally on this tree totilde. So in order to do that, I'm going to proceed in 3 steps. So first, I'm going to explain you how do you construct this tree coded by the local time. Then I'm going to do a bit of a detour, or seemingly of a detour, and I'm going to discuss the notion of boundary measure for excursions. Okay? And finally, I'm going to explain how these two notions relate, and we will obtain this description for the joint distribution of the excursions and the tree of local time. So again, this description was obtained in the Brownian case by Gall and Abraham in the work of 2018, but the description that we obtain is actually a more precise version of the work of Abraham and Gall in the Brownian case. But ours works in much more general settings. But again, the tools that we use to prove these results are completely different to the ones of Abraham and Gall. Okay, so let me then start by explaining what is this tree coded by the local time. So to construct this tree, we rely in a notion which is very general of subordination of trees, which is due to Gall from another work of 2018. It's not the same one as the one with Celine Pam, and which actually can be traced back in the setting of superprocesses in different forms in a work of Bertoin, Gall and Le Jan in 1997. So let me then explain how this works. So remember that we denote by I for the set of points in the tree at which the motion takes the value 0. And now the goal, remember, is to construct a tree, totilde, which encodes the genealogy of the set of points. So informally, it is very simple to understand how you should construct this tree. Basically, what you want to do is you want to get rid of all the black components on the original tree T, so that you end in the end with an object which is only made by yellow points. So informally, what you want to do is you want to consider each excursion component and collapse it in a single point. Okay. So for example, here I have one excursion component CU, and then I'm going to identify it in a single point, and this is what you see in the right. So if I do this for all excursion components, I'm going to get rid of all the black points, and I will obtain this object, which turned out to be a tree again. Okay. So a bit more formally, so if you're familiar with how trees can be called by continuous function, this might seem familiar. So what we do is we define a pseudo metric in the original treaty in terms of the local time process. So for any pair of points A and B in my starting treaty, I define a pseudo metric at A and B by this formula. So I look at the value of the local time L at A plus the value of the local time at B minus 2 times the minimum taken by L in the geodesic path which connects A and B in the treaty. So in particular, notice that if I pick 2 points A and B which are in the same excursion component from these two, well, then the local time process is constant along the geodesic path which connect these 2 points because the Brownian motion is not taking the value 0 in this part. So the pseudometric is going to vanish for those 2 points. Okay. And then what I will do is I'm going to identify then any pair of points as which this pseudometric vanishes. And if you do this construction, you consider this gives you a quotient space, which is defined, this is totiled. And this totil equipped with this DL, which is now a metric, is a tree. And this is what I'm going to call as the tree coded by the local time. So the reason why we call it as, like this is because the distance of points to the root of the tree totiled are coded by the value of the local time at the corresponding point. Okay. So this tree in some sense really codes the genealogy of the yellow points in my original treaty and get rid of all the additional structure. Okay. Okay, so very quickly, some properties that we know about this tree totiled. So the first one, which I think might be surprising, is that it is a Lévy tree. So the fact that it's a tree is really a topological argument, but in fact it falls again in the class of random trees that we are working with. It's a Lévy tree, and then it has a Laplace exponent, and we denote this Laplace exponent by psi tilde. So this Laplace exponent, one can show that it has no Brownian component, and in the Brownian case, actually all branching points are branching points of infinite multiplicity. Okay, so this is okay. And now, well, for each of these branching points of infinite multiplicity, one can define, and this is thanks to general properties of Lévy trees that were explored in works of Duquesne and Gall, one can define a notion of its fractal size. Okay, so this is for each branching point of infinite multiplicity in the tree totil. I define a notion of size, M of A, according to the following formula. So let me explain. So I'm fixing a branching point of infinite multiplicity in the tree totil, and I'm going to, for epsilon fixed, I'm going to look at how many subtrees I have rooted at this point A that reach a height larger than epsilon. So in my representation, I only have 2 of these trees. But if I let epsilon go to 0, well, because the tree is, the branching point is of infinite multiplicity, this number is going to increase as epsilon go to 0, and it's going to blow up. So for example, here I have now actually 6 subtrees which are rooted at U and that reach a height greater than this gap epsilon. So this quantity blows up, but when you renormalize it appropriately, it converges towards a positive variable that I'm denoting by M of A, and this is what I'm going to call the fractal mass at the point A. And this is a general property of Lévy trees. So this is not something just inherent from the tree totil. Okay. So with this, I have everything I need about this tree of local time. And now I'm going to then move to this kind of seemingly different topic, which is the problem of constructing a notion of boundary size for all excursions away from 0 of my Brownian motion, or more generally, a notion of boundary measure for excursion of my Markov process of choice. Okay. So first, what is the boundary of an excursion? Well, I'm going to define the boundary of an excursion component CU as a set of points in CU which are leaves for CU, but which are interior points for the tree to H. So for example, this point that I'm looking at here, this is a leaf for CU, but it's an interior point because it has descendants in the tree. Okay. But for example, this point here, this is a leaf for CU, but it is as well a leaf for the tree. So this is not part of my boundary. So we really want points which have descendants. Okay. So again, in my picture, this looks like it's a very simple set, but this is again a very complicated subset of the component CU. And the goal is to obtain some sort of notion of size for this fractal set. So how do we proceed? Well, first, thanks to the fact that we have this Poissonian description for the excursions, it's sufficient to show that we have a notion of boundary size under the excursion measure n bold star. Okay? If we define a notion of boundary size under n bold star, automatically we have this notion of boundary size for all excursions for my tree-indexed process. So thanks to our Poissonian description for the excursions. But even more, well, we know that this measure n bold star is just the push forward, or the law, if you want, of the truncation of B under n bold. So now, instead of working on the n bold star, I can define a notion of boundary measure under n bold, which depends, and this is crucial, which depends only on the truncation of B. Because if my notion of boundary size depends only on the truncation of B under n bold, then automatically it will work under n bold star, and if it works under n bold star, we have it for all excursions. Okay? So the advantage is, again, that this measure n bold is extremely simple. So working with it is easy, while working with n bold star, well, a priori, it might be difficult. So this simplifies the task. So that's what we're going to do now. So define a notion of boundary size under n bold, which only depends on the truncation of B. So here, I'm working on n bold, and again, I use the notation I for the set of points in the tree T, at which the motion takes the value 0. So under n bold, I will be denoting by C0 for the closure of the connected component of the complement of I, which contains the root. So remember that under n bold, by construction, we start with some sort of big excursion away from 0, which I am doing the contour of. And afterwards, we have this kind of paths that live afterwards. Okay. So C0 is this big connected component, if you want, the excursion component, the big excursion component of n bold. So here I have trimmed everything which is not in C0. Okay. So in particular, the restriction of B to C0 is the truncation of B. Okay. So again, I have my usual description, representation of n bold, and I want a notion of boundary size so basically a notion of size for this set of yellow points. So in order to do that, we're going to proceed by some sort of approximation. So I'm going to fix epsilon greater than 0, and I'm going to look at the volume of points inside C0. So again, this is crucial, for which the motion B takes values smaller than epsilon. So I'm looking at the volume of this portion, if you want, of my motion. So this, when it's normalized appropriately, is converging as epsilon goes to 0 towards a positive variable. Okay, and this is exactly what I'm going to call the boundary size of the excursion associated to C0 under n bold. Okay. So one of many important properties of this measure of this boundary size set sigma is that it allows to decompose n bold in two parts. So let me explain, and this is what I'm calling the special Markov property. So I'm going to note by Bi and Li for the restrictions of B to the connected components of the complement of C0. So again, let me explain the picture, which is clear. So the Bi's and Li's consist in these paths, which are rooted at yellow points. Okay, so those are the paths that have, if you want, survived the return to 0 of some of these paths and have lived afterwards. Okay, so they are dangling from yellow points, and we have infinitely many of them. Okay, so these are the Bi's, and the Li's is just the corresponding value of the local time. So I will consider this family, and I'm going to store them in a point measure. And we showed with Armand that conditionally on the boundary size set sigma, this is of very simple nature because it's just a Poisson point measure, and the intensity is just n, so the law of Brownian motion except for the Brownian tree, multiplied by the boundary size. So informally, this is telling us that conditionally on the boundary size, these subtrajectories are independent Brownian motion except for the Brownian tree. Okay, so that's the. So this result is really crucial because it allows you to decompose n bold in two, and this is telling us that what comes after these yellow points is extremely simple. Okay, so this is a very useful result. Now, getting back to what we were doing on the boundary, our notion of boundary size. Remember, we looked at the volume, but only inside C0. So in particular, our notion of boundary measure only depended on the truncation of B under n bold, and therefore is well defined under n bold star. So the notion of boundary measure is well defined under n bold star, and then by using our Poissonian description of excursions, we deduce that for all excursion BU star, we have a notion of boundary size set sigma u, and this set sigma u satisfies this approximation. Yeah. So now we have a notion of boundaries for all excursions under n and under p. So to sum up what we have done up to this point, so under P and under N, we said first we constructed this tree totil that we call the tree coded by the local time, which calls the genealogy of the yellow points on my starting totil. We said that all branching points are of infinite multiplicity in the Brownian case, and we have defined a notion, we use the theory of Lévy trees to define a notion of fractal mass at branching points according to this approximation. Then, on the other hand, we define a notion of boundary size for all excursions according to, again, another type of approximation. Okay? We depend on the excursion component. And now, finally, I can state a result which puts everything together and allows us to obtain a description of the law of the excursions conditionally on the tree of local time. And this is the following theorem. So under P and under N, and this is important, now this result holds under P and N. For each excursion component CU, I'm going to denote by U in brackets for the corresponding point on the tree tilde, which is associated to CU. So remember that when we constructed a tilde, we took components like CU, and we identify them in a single point, and this is exactly U in brackets. Now, we proved that actually, so for all debut U's, the point U obtained by identifying the components U in a single point is a branching point of infinite multiplicity of the tree totil. And even more than this, it's a one-to-one correspondence. So all branching points of infinite multiplicity in the tree totil come from collapsing an excursion component in a single point. So this is already telling you that the tree totil is very closely related to the excursions because each branching point for infinite multiplicity is associated to exactly one excursion, and it is coding the genealogy of the excursions. But of course, you lose the excursion itself because you have collapsed the excursion components. But even more, which might be more surprising, is that we have the following equality. So the fractal mass at the branching point U is equal to the boundary size of the corresponding excursion. So this is, I think this is surprising because, well, first, these two objects were defined in very different ways. The boundary measure, set sigma U, was defined in terms of information from inside the excursion component CU. But the tree totil, well, we constructed by removing all these components CU. And this notion of fractal mass was defined in terms of tree totil. So a priori, there is no reason why these two notions should match at all. But this is telling us that when you collapse excursion components, the boundary size is not lost, and it is encoded exactly by the sizes of the branching points of the tree totil. Yeah. And that, more or less as a consequence of this, one can deduce that conditionally on the tree totil, the excursions are independent, and their law is just the excursion measure conditioned to have boundary size equal to the corresponding fractal mass. So in this picture, I sum up essentially the theorem. So you have the tree totil, which codes the yellow points. Branching points are in one-to-one correspondence with excursions of our tree-indexed process. The fractal mass at each branching point equal exactly the boundary size of the corresponding excursion. And conditionally on the tree totil, excursions are independent between them, and their law is just the excursion measure conditioned to have as boundary size the corresponding fractal mass. So this is really the analogous result to the one I have described before with the inverse local time process and the excursions in the time indexed setting. Okay. So I think with this, I'm going to stop. So thank you very much for attending and for listening to my presentation.
Thank you very much, Alejandro.
No, thank you.
Over here. Any questions?
I have there's a question, the following. People in this seminar is very discreet. So I would like to know if you have this beautiful structure appears also in just symmetric random walk.
Yeah, so in the discrete setting, you would consider like a Galton-Watson tree. And on top of it, say a symmetric random walk. And then you can define the same structure. So you could define the notion of an excursion component and an excursion. And you can define as well this tree totil, because you can collapse excursion components in single points. And what you would obtain is a Galton-Watson tree as well, which would be the totil if you want, but in a discrete setting. Indeed, yes. So the same type of games still hold in discrete setting.
Okay.
Or should at least.
They should. And would you convert one structure to the other?
Sorry?
If the discrete structure would convert to the continuous one in some discrete.
Yes. So some sort of convergence. So, I mean, we know convergence of tree indexed processes in discrete, like Galton-Watson trees with labels towards Brownian motion indexed by Brownian tree, or more generally, yes. So these type of results do exist. A more precise conversions where you take in like you consider maybe the tree indexed process and the tree total jointly. I don't think this has been done. But yes, it is a very natural thing to look at now that these type of results are there. Yes, indeed.
Thank you.
Also,
Thank
would
you.
you be able to compare the laws of the Galton-Watson trees? I mean, somehow.
Sorry, I couldn't.
If you start with the one Galton-Watson tree, I mean, whatever you get in as a result of the construction, would you be able to compare the laws of the reproduction laws of the?
Between the two,
Yeah, you know, to get some kind of simple.
Yes, I think you can have some sort of somewhat explicit description for the reproduction law. It's not going to be a nice one at all. At least, I mean, maybe if you consider a simple random walk, it will be, but more generally, it will not. So in our case, we do have a description for the branching mechanism, Título, but I mean, it's semi-explicit. I mean, we have a formula for it, but in most cases, it's not like you cannot really. It's not described in the usual way if you want. But in some particular cases, when, for example, in the case of Brownian motion indexed by a stable tree, the formula is completely explicit. You get a stable branching mechanism. So in the discrete setting, I expect that in some examples, you can obtain explicit descriptions, but in general, it will not be an easy, an easy to see description of the reproduction law.
Okay. Thank you.
So, thank you.
I wanted to ask a question.
So I don't think I have a sound.
No,
Okay, so
We don't listen.
we can't hear you.
No te escuchamos, Miki.
I cannot listen. Sorry.
no.
Go ahead, Milton. I think it was working.
So can you hear me? Yes. No.
Yes.
Okay.
Thank you.
My question is the same line of Pablo. Is that one of the I mean, in my head, one of the nice things about this this description of excursions in terms of these Poisson measures is that allows you to prove convergence, because it's difficult to prove convergence directly. So I was wondering if you can do the same for the if this type of structure actually helps you to get the convergence of the discrete object to the continuous objects. I mean, especially about the local times, because the local time to prove that the local time of the random walk converges to the local time of the Brownian motion in general is very difficult, no? And this type of structure helps a lot to prove the type of theorem.
Yes, yeah, this is a very good point. So actually, yes. So one thing that it's important that we think is going to have an impact is this description in terms of the measure n bold, because I mean the measure n bold star had appeared. I mean, in terms of the excursion theory of Le Gall had appeared before, but it was not well understood at all. So the problem is that if you want to show convergence towards something which is described by n bold star, this is going to be essentially impossible because you don't understand n bold star, so it's kind of hopeless. But now that we know that the n bold star is just a truncation of n bold, well, showing convergence towards n bold shouldn't be difficult, because n bold is a Brownian tree with on top of it a tree indexed process, which is very simple. Convergence towards Brownian trees is something which is very well understood, and then convergence towards this, I mean, kind of Markov process again should be particularly complicated. So we expect that this should help a lot towards convergence towards objects which are encoded in terms of the measure n bold star. So in Brownian geometry, for example, you have the so-called Brownian disks, which play a very important role in the theory, and which are exactly encoded on the n bold star. So we think that this should help in this direction quite a bit. And concerning the local time, well, actually, the local time that we introduced, this process A, when you look at the total mass, A sigma, this is something which in the Brownian case, it has already appeared in the literature. It's the so-called integrated super Brownian excursion, the ISE. But only if you look at the whole mass. what we did is we now have a process which also measures the local time, but when you score the tree from left to right. So convergence towards the ESO, I think this is well understood. I mean, I think there's a lot of work on this already. But I would expect that now that we better understand how this works, it should be possible to obtain indeed a more kind of precise result when you have convergence of local time. Yes, indeed.
Okay, thank you.
Thank you.
Okay. So if there are no further questions, let's thank Alejandro again.
No, thank you. Thank you for the invitation. I was very happy to be here today.
And thank you for a great talk. And okay, I think we can.
Thank you, Alejandro. Very nice talk.
Okay. So
Thank you. Thank you.
let's meet again next week. And yeah.